course. Today I want to talk about cascades, and you will learn everything you ever wanted to know about Bayes' rule, conditional probabilities. It's a very probabilistic course today. First, a few seconds of respect for the people in Ukraine who are still fighting for their freedom and for our freedom. Okay, today I want to talk about dynamics. In the previous course we had things like traders, we had how things are, topology of the networks, things work. Now we want to see how the network influences people's behavior over time, dynamics. And the main thing is called cascades. Everybody knows cascades, and I will give examples, but you know cascades already. Cascades is when the decisions are made by a bunch of people, and you look at the other people, and you make decisions depending on how they make the decisions, okay? And there's two kinds of cascades. There's information cascades, that's what we're going to talk about today. There's also direct benefit cascades. We'll talk about that next week. And I'm going to give you a formal model, but you will see it's very intuitive. Huh? It's something that really everybody has already intuition on. Information cascades is sequential versus independent. If I make my decision without looking at anybody else, just by myself, then it's independent. But usually people don't do like that. They look at what other people do, okay? And this is sometimes good and sometimes bad. And that's what we're going to explain today. And I'm going to introduce a formal model, and we're going to do lots of computation, and it's all based on Bayes' rule, which you have probably already seen in a probability course, I hope, right? Bayes in French, I don't know, people will call it the règle de Bayes, but it's called Bayes because the guy is probably English, not Bayes' rule. So that is kind of, take some time to get used to it, and you'll see, and I will try to be very careful so that you understand things. Okay, so let's talk about information cascades. And the idea is people influence each other, and people like to follow the crowd. And I'll start with some examples, and then we'll go into a formal model. Okay, so an example of an information cascade is choosing a restaurant. Okay, let me turn this off first. Choosing a restaurant. You want to pick restaurant A or B. Either you go to a Japanese or Indian restaurant, and you have done your own research. You find restaurant A is very good. But you go to restaurant A, and you see no one is there. It's empty. And restaurant B is full of people right next to it. What do you do? Okay, it might actually be a good idea to join the crowd at B, maybe, and not follow your own research. If every diner has independently, that's the key word, decided that B is better, then collectively, yes, it might be a very strong argument, okay? And then you can choose B contrary to your own research. And if everybody does like you have an information cascade where it's like dominoes falling, everybody's doing the same decision. This is also called herding, because people behave like a herd of animals, all going in the same direction. Okay, so an information cascade, it can happen when people make decisions sequentially. That's the important thing. Sequential versus independent. So sequential, the later people will see what the earlier people did, and try to figure out, infer, why did they choose that? Maybe I should follow them. Okay, so a cascade occurs when people abandon their own private research in favor of what the other people did. Okay, it's not just mindless, it's actually rational. You try to understand the reasons why they did it, and you use their decisions to help your decisions. Okay, but still it can turn into weird results. Okay, so it's not the same as just peer pressure. Right? It's not just like peer pressure, because you're actually being rational. You're doing some kind of inference, deductions from the information you have. Okay? So there's two kinds of cascades, like I said before, information cascade versus direct benefit. So this all is the information, because it's the information that's the thing. The other one, let me just mention it now, the direct benefit is when more people do the same thing, it gives a benefit to everybody. Okay? When everybody uses Word, Microsoft Word, then it's very good to send Word documents, because everyone can read them. So there's a benefit for information exchange, because the more people use it, the more each person has benefit. Okay? In the olden days, it was fax machines, so I mentioned them, because this is also a history course. I don't know if you've ever used it. I used it a lot years ago. Fax machine lets you, it's like a copier, but the copy is done remotely over the phone line. But it's only useful if the other person also has a fax machine. If everybody has fax machines, it's useful. If you're the only one, it's not useful. So that's a direct benefit cascade. It has a benefit to you because more people are using it. So you align with the other people because you get a benefit from it. Okay, so that's not what we're going to talk about today. We'll talk about it next time. Today I want to talk about information cascade, where you look at the previous person's decisions. Okay? Okay, so how do we organize this? The formal model is kind of formal. In the usual tradition, I'm going to define a formal model, idealized. We did this already many, many times. And we will analyze this mathematically and to get some insight. Okay? And we apply then the model to realistic cases. But I won't start by that. I will start by some simple examples to give you really the intuition. The first one is a simple herding experiment, where people decide things in order. And then I will explain this one. We'll analyze it by using Bayes' rule. So Bayes' rule is a way to do inference with partial information. Okay? So it's called conditional probabilities. If I know something with some probability, but then something else happens, then this might change my probability. Okay? So I have my prior knowledge, and then if I get some more information, I'll have new knowledge. So that is called conditional probability. Okay? So we're going to analyze that using Bayes' rule. And so this is all going to be a bunch of probability calculations. And then, in the second part, I will talk about really a formal model, an idealized model, completely formal, and we will analyze it mathematically, and we will see exactly how cascades can arise. It sometimes doesn't arise, and sometimes it does. Okay. And then finally we'll see some conclusions. Okay, so let me start with the herding experiment. So this is a very simple kind of experiment, okay? And I started because all the concepts are there, because the formal model is kind of mathematical, so it's important to get the intuition. Okay, so you have to make a decision. So there's actually three pieces. One is that everybody has to make a decision. Two is that the decision the decisions are made sequentially, and everybody can observe the previous decisions. And 3, everybody has some private information to help them. So person 1 has private information and decides. Person 2 has private information, sees the decision of person 1, but does not know the private information of 1, but then decides. Person 3 has private information, sees the 2 previous decisions, and then decides, and so on. Okay, so that's how it works. And the experiment is very simple. There's a classroom with students and an urn, so kind of a big flower pot or something, with 3 marbles in there, and there's either red or blue, and there's 2 possibilities. There's either 2 red and 1 blue in there, or 2 blue and 1 red. So I don't know which is which. So there's always at least 1 of each color, but there might be 2 blue and 1 red, or 2 red and 1 blue, and these 2 possibilities each have 50% chance. So I don't know what it is, and nobody knows what it is. A student comes to the front, puts his hand in there, picks a marble, looks at it privately, puts it back, and then makes a decision. A public yes. Majority red or majority blue. Okay? Then the student sits down, and then the second student comes up, picks a marble, looks at it privately, puts it back, and makes a proclamation again. And the second student knows what the first one decided. Okay? So here's kind of what can happen if the students are thinking, what the reasoning. Okay, so let's talk first the first student. The first student, if the first student picks a red marble, then the student will guess red. That's logical, because the private information is red, so there's like 2/3 probability. So the probability that there's majority red, given that you picked a red, and there's some probability, and so it's greater than half. So he guesses what he picks. Okay, that's easy. The second student, the second student picks a marble. If it's red, and the first student said red, and the second student sees a red, then he will guess that color too, because he knows 2 reds already, from the first one and his own red. If he sees an opposite color, so the first student said red, and he sees a blue, then it's like 50-50. He has 2 pieces of information, one that says red, one that says blue. Okay, so it's like a tie. But let's just say he will break the tie by just guessing one color, which is the color that he picked. Okay? So the first 2 students will actually tell what they saw. Okay? They give perfect information about what they have seen. That's the first 2. Now the third one, it gets interesting. Okay? Now it starts getting interesting. The third student picks a marble. Okay. Now it depends on what happened with the first 2. If the first 2 guessed opposite colors, red, blue, and the third one picks blue, then the third one will guess what he sees, blue. Okay. If the 2 picked opposite. But if the first 2 said the same color, then the third student actually has 3 pieces of information. 2 reds, for example, and 1 blue. Okay? So the third one, rationally, the highest probability of getting it right is to say what the first 2 guessed. So if the first 2 guessed red, and the student picks blue, the third student will say then red. Okay? And now it's a cascade. Now everybody after that is going to say red. Even if they see blue, they're going to keep saying red. Everyone will forever say red. Okay? It doesn't happen if it's opposite. Okay? Now let's take a look at the fourth student. But for now, let's make it simple. Let's take only the case where the first 2 have guessed the same, and the third has said the same, okay? If the first two guess the same, then the fourth and later will all guess the same. But notice, only the first two guesses are giving real information. Okay? Real information about what's in the urn is only coming from the first and the second. The third one is no information. Okay? The third one will always say the same as what the first two say, so there's no extra information. Only the first two are giving information. Okay? So that's the case of the same, or the first two are the same. What happens if the first two are opposite? Well, then the third one will guess what he sees, and then we do have information. We have blue, red, blue, or red, blue, red, or that's it, something like that. And so it's not yet a cascade. Okay? Maybe a cascade will start, or maybe it still goes on for a while. So basically what happens is, you can have it be kind of fluctuating, and then all of a sudden, boom, a cascade starts. Okay? So that's kind of the intuition, and our formal model is going to explain it. Okay? So let me first make some general conclusions before we go into the formal model. So first of all, cascades is very, very easy to happen. Okay? You can lock in a decision with very little information, very fast. And the students are completely rational, huh? They are reasoning, they're not guessing, yeah? They are doing rational inference. And it's very easy. The second conclusion, that cascade can be bad. It can be wrong. Okay? So let's say you have a majority red urn. The first two students, they might say blue. Blue, blue. There's 1/3 times 1/3. There's 1/9 chance that the whole thing is wrong. Okay? That thousands of students are saying blue, and it's actually majority red. Okay? So a cascade doesn't have to be right. It can easily be wrong. And final conclusion, it's actually very fragile. It's like a building built on very shaky, thin foundation. And a little bit of cheating can break the cascade. So let's say we have a long run of blue, 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 and get up to students number 50 and 51, and they both see red, but they cheat. They show their red marble. They say, look, I have a red marble. Okay? That actually gives extra information. I mean, it breaks the rule, but it gives extra information. And student 52 now has 4 pieces of information. Okay, the colors of 1 and 2, but nobody else. And then the colors of 50 and 51. 4 pieces of information. And it could be blue, blue, red, red. And so there's again a tie break, and so the cascade is broken. So it's very easy to break a cascade. Okay? The initial run of 49 blue guesses has very little information in there. So cascade, it can be wrong. It's very easy to make it. It can be wrong, and it can be fragile. Okay, so let's study now. So that's kind of all very intuitive. Okay, now we get more and more formal. And to do that, let me first introduce a little bit of probability. I'll talk about Bayes' rule. So we're going to use Bayes' rule the whole time. Everything is built on top of Bayes' rule. Okay? So you've seen Bayes' rule, right? Huh? And of course, you understand it very, very well, and you remember it very well. Well, I doubt that, so I'm not going to assume that you understand it very well. So I'm going to introduce the idea. Okay, so first of all, it's going to be about conditional probability. So what is the probability of X, something, given that I know Y and the previous person said Z? Remember, there's the previous decision, and then there's the private information. So what is the probability that the urn is majority red, given that I picked a red and the previous person said blue? So you have to calculate probabilities based on pieces of information. You make decision when you have partial information, okay? You have you know something, and it helps, and you have to figure out how to use it. And this is Bayes' rule, okay? So we're going to compute probabilities. So probability is a kind of funny calculus that calculates numbers that somehow correspond to how likely things are. And let me define a simple definition. So an event is a set of possible outcomes. So an event is, for example, picking a red marble. So whenever I do with 3 students, every time the 3rd student picks a red marble, that's a set of outcomes, and that's an event, okay? And the sample space is all possible things that can happen, all possible outcomes. So an event, and I'll call it A, event A is a subset of the sample space. Some of the outcomes are where I pick a red marble, okay? And this event has some probability, which is a number between 0 and 1. You can kind of interpret it, the fraction of outcomes in which event A occurs when we repeat the experiment an arbitrary number of times. Okay, so I'm not going to do much philosophizing about what this means, but we're going to compute things. Okay, so here is a sample space. So this is a Venn diagram. In this rectangle, there's lots of events, little dots. I'm not showing, but they're all over. And event A is a region in this space. It's a set of all outcomes where something particular happens, picking a red marble. And there's another event B, and they intersect. And this is the joint event where both happens. For example, the first person picks red, and the second person picks blue. So A intersects B. And we need to calculate probabilities when we have some information. For example, we have a probability to have a red marble, or we have a probability that majority red, but what is the probability of majority red given that I have picked a red marble? Okay, this is called conditional probability, and B is partial information. So I know a little bit, and it changes my guess, my estimate about A. So we'll write it as probability of A given B with the vertical bar. Probability of A given that B has occurred. This is very important for the whole cascade thing. Okay? Okay, so the main mathematical thing we're going to use today is called Bayes' rule. You can actually compute the probability of A given B. It's the probability that both of them occur, joint event, divided by the probability that B occurs. Okay? So it's probability of A intersect B divided by the probability of B. And you can, in the same way, switch them. And this is very interesting. The probability of B given A, it's the opposite direction. And this gives us a similar formula. And now we can compute the conditional A given B in terms of B given A by just doing a little bit of algebra. And this gives us a really interesting rule. It's actually very powerful. It seems to be simple algebra, but actually it's very powerful because there's some causality there. So, for example, this is the probability of A. Okay, so I have some knowledge, probability of A. And then B happens. B happens. Then I have the probability of A given B. So I add something. I add B, and the probability of A changes. It goes from A to A given B. This one is called the prior probability. This is when I don't know anything. And this one is called the posterior probability. It's when I know that B has happened. And there's this correction factor here, the probability of B given A divided by B. And so this lets us go from prior to posterior. It lets us update probabilities when we know more information. Okay? So this is very important rules. I'm going to write it on the board here and leave it here today. So the posterior is A and then you have this correction factor. So this is the prior probability in terms of Bayesian analysis. So there's something called Bayesian analysis. This is an analysis where you take new information into account and you update your knowledge. Okay? And this is the posterior probability. And this one is some correction. When B happens, you have some correction factor that comes in. Okay? So this is Bayes' rule, and you've seen it already, but we're going to use it a lot. Okay. I want to give two examples first of Bayes' rule, because Bayes' rule is very important in everyday life, actually. And when you read newspapers and see the news and so on, very often people make really stupid mistakes in guessing probability. And because they don't use Bayes' rule in the right way. So I'm going to give two examples. The first one is eyewitness testimony. When something happens, an accident, and you have witnesses, they see things, but they're not completely reliable. Okay? So the probability of something depending on some private information. But the private information is not completely reliable. Okay? So let's say in this city, let's say Gotham City, to pick a name, 80% of the taxi cabs are black and 20% are yellow. Okay, the color of the cab. That's an objective number. And there was a witness to a hit and run accident. He saw an accident and there was a taxi in there, and he says the taxi was yellow. But of course, it's all very fast and he's confused and so on. So witnesses are not 100% reliable. They sometimes misidentify. But if the taxi is yellow, they will say yellow 80% of the time. But if it's black, they will also sometimes say yellow, which is weird. But they will say black 80% of the time, but they will still say yellow 20% of the time. Okay? Because, things happen very fast. There's noise, sirens, many cars. Maybe there is a yellow cab over there. Other cars have different colors. So they sometimes make mistakes. Okay. So let's say the witness says yellow. I saw a yellow cab. What is the probability that the cab really is yellow? That in real life, there really was a yellow cab. It's clearly not 100%, okay? Witness can make mistakes. And there's also this proportion. To calculate this, we can use Bayes' rule. So we have here the true color is yellow. The probability that the true color is yellow, given that the witness reports yellow. So the probability that the true is yellow by itself is 20%. But now we have extra piece of information. The witness says it's yellow. So what is the new probability? What is the posterior probability? See, this is Bayesian reasoning. Adding extra information into your reasoning. Okay? So let's compute it. We can compute this using the magic of Bayes' rule. Okay? We want to know the probability that it really is yellow, given that the witness says yellow. According to Bayes' rule, this is equal to the real probability, the probability original prior probability multiplied by this correction factor. Okay? So the correction factor is, what is the probability that I report yellow if it really is yellow, divided by the probability that I will report yellow. Okay? But these numbers can all be calculated. But this is one it's not easy to calculate. But with these numbers, you can calculate those. Okay? The probability that the true color is yellow in the absolute is 20%. Okay? The probability that I report yellow, if it's yellow, that's 80% chance the witness is not making a mistake. This bottom one is a little bit more complicated. What is the probability that the witness will report yellow? Well, there's two cases. It's either a yellow or a black cab. Okay? In the case of a yellow cab, it's the probability that I report yellow if it's really a yellow cab, but only if it's a yellow cab. I have to multiply by this percentage, okay? Because this only happens in a certain fraction. And I have an independent event, so I can do addition. The cab might actually be black, but I still say yellow. So this has some probability. And then there's a true probability that it's black. So this one is 80%. This one is 20%. This report yellow, true yellow is 80%. Report yellow, true B is 20%. So the probability in the abstract, if I see a random car, random cab, I will say it's yellow 32% of the time. Okay, but now I can compute the probability of that it was really a yellow cab if I report it as yellow. So you compute it, so you take this 20% number here, and you apply the correction factor. And you see the correction factor is bigger than 1. So this number goes higher. Okay? So that means that the witness report has increased the probability that the cab is yellow. So it increases our belief that it's yellow. So it's useful. Okay? The witness you report has substantially increased our belief that the cat is yellow, since without that it would be just 20%. You see? So because of this correction factor, it's sometimes less than 1. Huh? It's not always greater than 1, this number here. Huh? This correction factor, we have increased our belief that the cat is yellow. Okay? So this is interesting, but it's still only 50%. Huh? You could say if it's yellow, the witness will say yellow 80% of the time, but there's also a chance that it's black. So this is not 80%, huh? It's less, huh? It's only 50%, okay? So this is an important kind of a computation, and this is done a lot when you do forensics. Okay, let me give another example closer to computers. Spam filters, okay? Spam filters really use Bayes' rule a lot, okay? For email spam. So let's say you have a piece of mail that you get, and the subject of the mail says, check this out. Question, what is the chance that that's a spam? What is the probability that it's spam? Okay, again, it's conditional probability, huh? I have, first of all, the absolute probability of spam, but here it's conditional. I receive the check this out message, and I want to know what is the probability of spam. So spam, given that I have this. So it's again a conditional probability, yeah? And to compute this, we need some general information. For example, how much spam do you get? So clearly this number is coming from a whole time. I'm sure that it's more than 90%, if you look at, but let's say it's 40% of all the mail you get is spam. And the spam messages have 1% chance of saying check this out. And the non-spam messages have a little bit less chance. We need these numbers are all measurable. These numbers you can all measure, and the spam filter will have tables will know all these numbers. Okay? So with these numbers, again, we can use Bayes' rule to figure out the posterior probability. Okay? Again, the probability that it's spam, given that, check this out, following Bayes' rule, it's the prior probability of spam multiplied by this correction factor. So check this out, given that it's spam, over check this out. Okay, we can compute all this. So the denominator is a little bit more complicated. So check this out can happen both in a spam and non-spam case. If you compute that, it gives you 0.0064. So the probability of being spam, given that it's check this out, is 0.625, 62%. Okay? Notice that the prior probability was 40%. So this, check this out, has increased the probability of it being a spam. And this is called a signal. It doesn't prove that you have spam. You have to check this out. But it will increase the probability. So it's like a signal pointing to spam. Increases the likelihood that the message is spam. So a real spam filter will have many independent signals, and if a lot of them are increasing the probability of spam, by using Bayes' rule, then you could be almost sure it's really spam. This works really well. A good spam filter is extremely precise. Okay? If you combine a couple of dozen of these signals, and they're independent, then the chance that it's spam, given that that all these signals are true, is going to be very high. Okay? So you can see, again, the use of Bayes' rule in updating from prior to posterior. Okay? Okay, now we go a little bit farther. So now you know Bayes' rule, right? I refresh your memory. Now we're going to use it in this earning thing, with the urns and marbles. Okay. In the herding experiment. So each student decides majority red and majority blue. Okay? But it's conditional, depending on the information the student has. It's all information. And so every student is doing the following computation. The student will say majority blue given the information they have. And they will say majority blue if this is greater than a half. Okay? And then majority red will be less than a half. So the student should guess majority blue if this probability, this conditional probability, is greater than a half. And what information does a student have? We'll see here. Okay. So what do we know in our example? First of all, the probability of majority blue and majority red is a half. This is the initial thing. Either 2 red and 1 blue, or 2 blue red. It's half and half. So that either of those is 50%. The probability that you have a blue, given that it's majority blue, is 2/3. Because you have 3 marbles and 2 of them are blue. Then, okay? And the other case, probability of red given majority red is also 2/3. So we know these numbers. And with these numbers, we can guess this. For the first student, for the second student, for the third student, and so on. Okay? So how should the first student guess? The first student, let's compute the probability of majority blue given blue. So the first student has a blue marble. So the first student computes majority blue given blue. We use Bayes' rule. Again, we will update the prior to give posterior. Prior, majority blue is 1/2. But what is the posterior? Okay? So the posterior is this correction. The probability of blue given majority blue divided by the probability of blue. You can compute these, huh? So I'm not going to compute all of them by hand, but you can compute them. So the probability of blue, it's a combination of two things. It's either I pick a blue and it's majority blue, or I pick a blue and it's majority red. Okay? So this is a combination of two things. Very similar to the previous example, huh? Previous examples from the span, huh? This denominator, the probability of blue, there's two possible cases. Majority blue and majority red. If you compute that, in the absolute, the probability of seeing a blue is 1/2. Okay? And then the probability of having majority blue, given that you pick a blue. So I pick a blue, and what is it? Majority red or majority blue? Well, it's 2/3. If you compute it. So the prior probability of 1/2 has become 2/3. So the student should say blue, because 2/3 is bigger than 1/2. Okay? What about the second student? Well, the second student has to compute this. So let's say the second student also picks blue, sees a private blue marble, and the second student knows the first student has seen a blue. So this is the probability that the second student has to compute. What is the probability of majority blue given blue and blue? First student blue and second student blue. This one, again, you can compute using Bayes' rule. This one I will leave as an exercise because we're going to do more computation today. This is a very simple computation. So you again use Bayes' rule. You have this thing, huh? The correction factor with the probability of blue, blue, given majority blue. Assume these are two independent events. Then the probability of having both of them is the product. So it's blue majority blue times blue majority blue. The blue events are independent, and you can keep computing and then calculate this. Okay? Exercise for you guys. Okay? And you can keep going on that. Third student. So I have some, let's see. So the first two students are getting real information. They pick a marble, blue, and their decision depends on it. But the third student might be cascading. Okay? So the third student is where it gets interesting. So let's say the first student have picked blue, and the third student picks red. And so the third student has 3 pieces of information. Okay, blue, blue, red. So the third student has to compute this. What is the probability of majority blue given that first picked blue, second picked blue, and third picked red? Given 3 pieces of information. Okay, so you can use Bayes' rule for this. So I can do part of that. Majority blue, given that we have blue, blue, red. This is the probability of majority blue. This is the prior times a correction factor. Probability of blue, blue, red, given majority blue. Divided by the probability of blue, blue, red. Like that. Now we can compute this. So this one here, probability of B, B, R, given majority blue. So these are 3 independent events. Okay. So it's probability of blue given majority blue times blue given majority blue. There's lots of little computations going on here, right? Red given majority blue. So this one, probability of blue given majority blue is 2/3. This one is 2/3. Red given majority blue is 1/3. So this is 4/27. Okay. Now I also need to calculate this. There's two possibilities. It's either majority red or majority blue. So I have this case or I have the other case. And so I do the computation. I turn it around, and I get 3/27. The magic, the wheel has stopped there. And so Bayes' rule will give me majority blue, which is 1/2, times 4/27 over 3/27. So this is 2/3. Okay? It seems very intuitive, huh? But be very careful on intuition when you do probabilities, huh? There's some famous problems that are totally counterintuitive. So here, the probability of majority blue, given I pick blue, blue, red, is 2/3. That means I should guess majority blue. Okay? You see how it works? Okay. So that's all introduction to the model. Now we go to the model. I like the way the book calls it a simple model. You will tell me whether you agree that it's simple. Okay. Now we make a simple model. But let me make a summary of it on the board. That will make it easier. Keep track of it. Okay. So the simple model. Now we're serious. Now we're going to make our formal model and work it out. So the model, we have to decide. You decide on an option. You have to decide whether to accept or reject the option. Okay? I want to buy a refrigerator or anything. So this is like the internet cascade. Huh? So this is not the majority blue, red anymore. Huh? I have an option. I want to reject, and I have 3 things. So the world that I'm in has 2 possibilities. It's either in a G state or a B state. In the G state, accepting is good. In the B state, accept is bad, but I don't know which one it is. Okay? Is it a good quality refrigerator that I want to buy? Well, the first 2 people that bought it, they're happy. So maybe it's good, but maybe it's by accident they're happy. Maybe it's a bad refrigerator. So the world is something I don't know. So this is unknown. It's either in a good or bad state. And I want to accept. And in the good state, accepting is good. And in the bad state, accepting is bad. Okay? And there's some probability that the world is in a good state. And there's a probability that the world is in a bad state. Okay? And I don't know. Okay? I have to decide whether to accept or reject. This will help me decide. So instead of a probability being bigger than 1/2, I'm going to compute some kind of payoff, which is telling me, is it good to accept or is it good to reject? Okay? So, if I accept and the world is good, then I get a VG payoff. Okay? And if the world is bad, I get a negative payoff. Okay? And actually I'm computing the payoff just for accept. So I'm going to say, I'm going to compute whether it's good to accept or not. Okay? And so there's some payoff that I'm going to compute. Okay? And there's some condition on this. Okay? So I'm going to assume that Vg times P plus Vb times 1 minus P is equal to 0. So basically what this means is that initially I'm neutral. So the relationship between Vg and Vb are related to this P. What is the chance the world is good or bad? Huh? So initially, the payoff is neutral. It's not positive, it's not negative. Okay? And then depending on, so that's kind of the prior, right? The prior is just 0 payoff. And then I'm going to see, when I get information, whether the payoff could go higher or lower, so whether I have to accept or not. And then I have some private information. This is the signal of the marble in my hand. H or L. H means that accept is good. Accept is good. Basically, the probability that H given G is greater than a half. It's going to be equal to, I'm going to say it's equal to Q bigger than a half. And it's L. It means that accepting is not good. Okay? So the probability of L, given that the world is bad, is going to be also, one can also call it Q. So I have some private information. So this is the marble in my hand. Okay? And the payoff is for the decision. So the first person will get a private signal, compute the payoff, and if it's positive, the person will accept, negative, not. The second person will get a private signal and knows the first person's decision and will again compute a new payoff and decide again. Okay. So this is the model, and with this model we can compute the whole general cascade. Okay? Okay, let me make a small break right now. And then I'll show you how it works. And I'll try to be very intuitive, though, because here we go from probability greater or less than a half. This model actually has a little bit more general. It's talking about a payoff. Huh? It's either going to be positive or negative. If I decide in the direction, if it's positive, then I decide good. If it's negative, I decide bad. Okay? On what the world is really like. Okay? Okay, let's make a small break. So it's not in the slides, but I think it helps to understand how it works. I have people, so person 1 is trying to decide, person 2, person 3, and so on. And each person has private signal, which is going to be something H or L, maybe H here. And then person 1 makes a decision. Accept or reject. Okay, for the option. That's person 1. Now we go to person 2. Person 2 also has a private signal. Get some private information, maybe L. That means it's kind of a recommendation to reject. And person 2 also sees the person 1 decision. So person 2 sees this and this. Okay? And then person 2 decides, maybe whatever, reject. Okay? Now person 3. Person 3 has some private information. Well, maybe H. And person 3 sees also some previous information. Person 3 sees this, and this. sees the previous decisions, okay, and this. And then person 3 decides, I don't know, accept maybe, okay. And then person 4 again has some private information, private signal, H, and person 4 also sees some information. So person 4 sees the previous decisions, these 3, plus this, and then person 4 will decide, whatever, maybe accept, and keeps going. You see that each person has their own private information, but they only see the public decision. So they don't know what the private signals are from before, okay? They don't really know. Because you don't know that in real life. You only see what they decide. You cannot read their brain, okay? This is inside their brain, and this is what they do publicly, okay? So each person sees the previous ones. Okay, so that's basically how the model works. Okay, so here, what I explained here is just what I put there. So the world, this is the basic thing. Initially, the world is either in a good or bad state. It's a good refrigerator or a bad one, or whatever, for some probability. So you don't know whether it's good or bad. And you try to kind of guess, okay? And the way to guess is you compute this payoff number. It's not really a probability, but it tells you whether to accept or reject, okay? So when you have no information, you assume it's like neutral first. And then you get information. So person 1 will get this private signal, and this private signal, H says, the world is probably good, okay, high. L says, the world is probably bad. Okay, so each individual, so I look at the refrigerator, it looks flimsy. Okay, I go to the store, it doesn't look good. That's my private signal. So this signal points, but it's still only probabilities, huh? So let's compute this now. I want to compute now all these probabilities. So here there's a probability, here there's a probability. So we can compute them. Okay, so let's compute them. Okay, so here's first the one signal case. This is person 1. Individual number 1 gets only the private signal. Okay? So how does it work? Well, before, when they don't know anything, we know this. Okay? The VG times the probability of good plus VB times probability of bad is equal to 0. It's neutral. But assume they get a signal H. Now we go from prior to posterior. PRG becomes PRG given H. PRB becomes PRB given H. So if I get the signal H, these probabilities change. Okay? These probabilities change, so this number, it's not 0 anymore. Okay? And if it's bigger than 0, then we can accept. If it's smaller than 0, we can reject. We can compute things using Bayes' rule. Now this gives us formulas that are a little bit complicated, but actually if you use a good intuition, it's not so hard. I'll show you. So G given H, that's G, that's the prior, posterior, times the correction factor. H given G divided by H. So what is this? Probability of G is P. H bar G is little q. Okay, we said it would be. The indication is that Q is bigger than half. So it's the H is kind of saying, yeah, it's probably a good idea to pick G. Okay. But then you have to do. So if you compute this, you have to divide it by probability of h now. So this one, remember the denominator of Bayes' rule, it's always two pieces. What is the probability of h? Well, the world is either g or b. So in the case that the world is g, we get this factor, h given g times g, and in the case the world is bad, it gives h given b times b. Okay, so this is the denominator, and here's the numerator. So we get this formula here. Okay, probability of g given h. Now, we have this denominator, which looks kind of complicated, and p times q. Okay, so I have to show you now the full formula, and I'll give you the intuition on that. And you'll see that actually, you don't have to actually calculate the values. You just have to know the directions, okay, how it goes. I'll show you how it works. Okay, so V, G, probability of G given H, plus VB, probability of B given H. So if we compute it, here we get P times Q, but in the other case, we will do it with B, okay? B given H, it'll be 1 minus P times 1 minus Q. And the denominator is the same. So we have this formula, which looks like this. PQ plus 1 minus P, 1 minus Q, VG times PQ plus VB times 1 minus P, 1 minus Q. We have this, okay? And we know, what we know is that VG times P plus VB times 1 minus P is equal to 0. We also know that Q is greater than a half. Okay, this is what we know. So what happens to this? Is it greater than 0 or less than 0? This number. And if we know this, looks very complicated, right? It's not actually so complicated. So Q bigger than half means that the H is pointing us to G, huh? And then we have the initial equilibrium kind of. The P, the VG and VB are making it so that we have a 0. So what happens? Well, look what happens. VG is actually bigger than 0. VB is less than 0, huh? So this Q is actually bigger than a half. And so 1 minus Q is less than a half. Okay? That means this number, VGP, is multiplied by something which is bigger than a half. And this number is multiplied by something which is less than a half. That means this one will get bigger compared to this one. Okay? This one gets bigger compared to this one. And this one is positive and this one is negative. So, what does it mean? Well, it means that this is going to be positive, huh? Okay? You see that? So it's not that complicated. It looks, when you do probabilities, it's very normal that you get formulas that look complicated for things that are actually intuitively sometimes simple. So don't be impressed too quickly. So the new payoff is greater than 0. That means the first person should accept. Okay? Right? You see that? Okay, we're not done yet, of course. Multiple signals. Okay. So we did only the first one. Now we do a bunch of signals. It turns out that when you have multiple people, each one gets a signal. So I get H, L, H, H. I get many signals. So I have a sequence of signals. Some of them are high, and some of them are low. Okay? I don't really care what order. Let's say there's A, high ones, and B, low ones. Okay? And S is this sequence of signals. So S would be something like H, L, H, H if we have 4, but it could be more. It turns out we can make a computation which is similar to the computation I do over there. Again, we have to do a conditional probability. What happens to G given S? Here I have G given H, one signal. But each time I add a person, I have another signal. So in the general case, I have S signals. And there's A high ones and B low ones. Well, it turns out that G given S is greater than probability G when A is greater than B. So when there's more highs than lows, then the sequence points towards G. Okay, that's kind of intuitive, huh? Since highs are pointing to G. So if there's more signals pointing high than low, then the probability of being good is higher. And if there's more signals low, A less than B, then we can compute this. And if A is equal to B, this is like indifferent. I have 2 highs and 2 lows, then I can compute this. So from this summary, when I have signals, S signals, A highs and B lows, I should accept when I have more highs than lows. I should reject when I have more lows than highs, and I have to do like tie-break when they're the same. Okay? That's very intuitive, but it's nice to have it be rigorously confirmed. Okay? So that's the summary when you have signals. Let me now do the computation, or at least part of the computation. Okay? Okay, part of the computation. So again, it's Bayes' rule, G given S. So the prior is G times the correction, S given G over S. So the probability of S given G, what is that? I have A highs and B lows in some particular order. High, low, high, high. Well, they're independent. Each signal is independent, so it's the product. So it's Q is the probability of high to the 8th power and 1 minus Q to the B power. Are you see that? I have A and plus B, A highs and B lows, and Q for high and 1 minus Q for low. And they're independent, so I do the product. I can also compute probability of S. Again, the denominator, there's 2 cases. As usual, you should be getting used to it now. The world is either good or bad, so we have to add the 2 cases together. This gives us a more complicated formula, is this. So P times Q to the A times 1 minus Q to the B plus 1 minus P times 1 minus Q to the A times Q to the B. And if we compute the whole thing, we get this. Oof. Okay, what happens to this when A is greater than B? Is it bigger than PG or not? Yikes. The looks hard, huh? We know that Q is greater than a half. Okay? Actually, there's a way to do it. Okay. So what was the trick? There was a simple trick. So there's a simple trick. You basically replace the denominator. This denominator, you can replace it by Q to the A times 1 minus Q to the B. Okay? q to the a times 1 minus q to the b. What does that do to this? Well, q is bigger than a half. Okay, assume now is a is greater than b. A is greater than b. So 1 minus q is less than a half. 1 minus q to the a is going to be less than 1 minus q to the a. And p, and so if I replace all this by just this, I will be increasing the denominator. Okay? So what happens then? How do you compare that to p? Well, I don't know. We'll see. Think about it. And I'll get back to it next week. Okay? You can do some simple reasoning. I don't want to spend too much time on this thing, but you have to be looking at q is bigger than a half, and a is bigger than b. Okay? So this thing, is it either bigger or less than pg? So if the denominator gets smaller, then it's bigger. If the denominator gets bigger, then it's smaller. Okay? But if you do the computation, it turns into this. Okay? So I would say, look at it, and I will come back to it next week. Okay? Fine? That's all we have to know. This is the summary of it, huh? Okay, I don't want to waste too much time on that. So now we get back to our diagram over there. Now we've done all the computations, all the things we need to do in order to really see when there's a cascade and when there's not. Okay? Okay, so let's see how it works. We have individuals, so they're deciding in sequence. They see what the earlier people do, not what they know. So they do not see the private signals of the early ones, only the decisions. Let's reason about the sequence and see when it gets to a cascade. Now we know the numbers. Okay? Okay, again, we start with person 1. Person 1 follows the private signal. So we know person 1 reveals the signal. The decision is actually the same as the signal. So we know the signal. Okay? Person 2 knows that. So it's like person 2 gets 2 signals. Their own signal and person 1's signal. And so we can use the sequence of signals. Okay? If the signals are the same, we follow what they are, HH. If they are different, then we do, the person 2 follows his private signal, so the tie break. So if it's HL, we'll do L. So person 2 will always follow their own signal, so they also reveal the signal. So 1 and 2 have actually revealed their private information. Well, that's important because then we can do some computation. So 3 knows that 1 and 2 revealed their private information, and person 3 has their own signal. So it's as if person 3 has 3 independent signals. Okay? And so person 3 will follow the majority. Okay? If person 1 and 2 make opposite decisions, person 3 will do the tiebreak. And future people will know that they revealed it. If person 1 and 2 make the same decision, person 3 will follow this, and future people will know that person 3's decision has no useful information. Okay? So you see the 2 cases here? In this case, there are actually 3 signals, and there's no cascade. In this case, person 3 is going to follow 1 and 2, and so we only have 2 pieces of information, 2 signals, and so the cascade has started. Okay? Let's now look at future people beyond person 3. Person n. Okay? With n greater than 3. So remember we have this case. Opposite and not. So assume that in all the previous cases, we're like here, that the person is always doing like a tie break, and we're not in a cascade yet. So we're not in a cascade. Now this is cascade, and this is not cascade. So that means all of these previous people have revealed their decision. Okay? All earlier people follow the signals. Person N knows this. And if the number of accepts equal the rejects, then N is the tiebreaker. Okay, that's reasonable. And now there's two more cases. If the number of accepts is just one different from the number of rejects, okay, either, there's two possibilities. N signal will make them equal, or N signal will make them more different by 2. Okay? And N will follow their own signal in both cases. So in the tie-break case, N will follow their own signal, and in the majority case, N will also follow their own signal. Okay? So basically, it's still information, the signal. But now we get to the interesting one. If the number of accepts is different by 2 or more from the number of rejects, then the private signal of N will change nothing. The majority, there's already a majority, okay? And N's private signal will not change that. And so this is where the cascade begins. So the cascade begins when the number of accepts and rejects is different by 2. If it's 1 or 0, then there's no cascade yet. If it's different by 1, the next time it can go back to 0 again, okay? But once it gets to 2, then we have majority and we cannot break it. So the cascade begins when the difference is 2 between the accepts and the rejects. So this is kind of a graph. So this is, I like this graph because it gives a good intuition. So here on the vertical we have accepts minus rejects. And here on the horizontal we have the decisions of the people. So 0, we have person 1 makes an accept. Person 2 makes a reject, so the difference is 0. Person 3 makes a reject, so it's -1. Person 4 makes an accept, so it's 0 again. Person 5 makes a reject, so it's -1. Person 6 makes an accept, so 0. Person 7 makes an accept, it's +1. Person 8 makes another accept, boom, and now it's 2. Now it's all over. As soon as the difference gets to be 2, the cascade has begun, and it can only get worse. Because starting from that, the decision will never change. Okay? A cascade begins when the difference between the accepts and the rejects reaches 2. As long as the number of accepts minus the rejects is at most 1, then each person will just be following their private signal and they will keep giving information. But eventually, when the difference gets 2, boom, cascade. So the cascade doesn't have to start right away, but it's going to start. It's very sure it's going to start sometime. It's highly improbable that this difference stays forever in this narrow interval, okay? As the number of people increases, the probability of a cascade goes to 1. Okay? Eventually you're going to hit this magic 2 difference. Boom, you have a cascade. Okay? So it can take a long time, maybe, but you will get it with very high probability. Okay? So this is showing us how cascades start. See, they don't have to start right away, but the probability of one starting goes to 1. Okay? Okay, so this is our model, the ideal model, simple model. According to the book, it's an extremely simple model. Okay? But in real life, things might be different. Maybe people don't see all of the earlier decisions. Okay? Or maybe people have different kinds of private signals. Or maybe the payoffs are different. So the real life can be more complicated. Okay? But the general idea is very similar. Okay? The trick is the following. When people see what others do, but not what they know, they don't see the private information, they only see their decisions, then you can have a cascade. Okay? Then you can have like a tipping point when you have a cascade started. And everyone is rational, so they're not being irrational here. Because if people would actually see all the private, if these would all be visible to everybody, then there would be no cascade. Because you could always make a decision based on all the signals. But it doesn't work like that. You only see what the people actually do. And as soon as the difference is 2 there, they will all lock in to the same decision, even though the private signals are different. So starting from this point, the information is fixed. You will have no extra information. Okay? So this is really the key thing. You see what others do, but not what they know. Okay? It's important for the intuition. Okay? So that's a kind of observation. Let's make now some lessons. So now we go down from Mount Olympus of the mathematical analysis. We go back a little bit to the intuition. Okay? So now we can kind of strengthen what we learned from the herding. First of all, cascades can be wrong. Okay? If accepting is a bad idea, but the first 2 people get high signals, some probability, even though it's a bad idea, the cascade will start, even though it's wrong. So again, cascades can be wrong, and it's highly significant. They can be, it's not very low probability even, they can very often be wrong. And cascades can be based on very little information. Their foundation is very small. Okay? Once the cascade starts, there's no more information. All you know is what happens before. All the private signals are only the ones from before. Okay? And final thing, cascades are fragile, and in the real world you can do that. If you see a cascade in the real world and you don't like it, the way to break that cascade is to give private information. Make the private information public. Okay? And that way you can overturn cascades. So this is a good lesson for real world. Even in politics, for example, people can be herding. But if information appears, you can overturn that. J'entends comme une discussion là. C'est pas normal. So a crowd can be wrong even if everybody is rational. Okay? Okay, now let me make 2 more kind of interesting conclusions of this. There is this notion called the wisdom of crowds. And there's actually a famous book by James Surovicki. And somehow he's like saying the opposite. He says if you have a lot of people together, aggregate behavior, sometimes they can be very smart. If you have a whole bunch of people together, and each one of them has only limited information, but they make somehow the decision together, like averaging the guesses of the number of jelly beans in a jar, that can be accurate. Okay? This is actually not contradiction, because the key is the independence versus sequential. Okay? What I said in the beginning. The key, this is true, a group of people can be very smart if you let them work independently. So for example, if you have a group of people and they have to decide on who is the winner in some kind of a contest, you have to let them make their own decision independently. If they can talk to each other, it breaks that and the decision is very bad. So it has to be independent. If they guess sequentially, or if they talk together, which can be even worse, then we are back in Cascades, and the result can be very bad. Okay? So the difference, if you have a group of people who have to decide, like a jury, in the Olympic Games, the judges are deciding their numbers independently, and they all raise their number at the same time. That's very important. That makes the result much more accurate. If they would be deciding sequentially, the result would be much worse, because then you could have a cascade. Okay? And let me end up with one thing, or one of the final things. This is something very Belgian. Okay? But you notice if you are working in Belgium. So one style, so you have group decision making. A bunch of people are in a meeting and they have to decide on something. What Belgians really love is called tour de table. I don't know if you've heard of that. As a person working in a Belgian organization, I see it a lot, of course, and it's considered very fair, but it's not really that good. So you go around the table sequentially, and everyone expresses their opinion on option A or B, for example. Again, this can lead to a cascade. Everybody, maybe they're initially favoring A. If a few people start by saying A, then the later people, again, even if they're completely rational, even without peer pressure, they maybe conclude that they also should favor A, but even if B is better. Okay? Or if they thought B was better on their own. So it's not social pressure. It's important to know. It's not peer pressure. They're being rational. Even without social pressure, you get cascades. So it's much better to get the opinions independently. Everyone writes them down on a piece of paper, for example. And then you bring the papers together, and then you, in the second phase, you show everyone's opinion. That's much better. Okay? This is a lesson from the cascading business. Okay? So you see, cascading is something that happens a lot. It's very interesting, Okay, so let me summarize what we saw. Try to give you some of the good intuition. Decision making in a group. The point is it's sequential. The second point is each person has private information and sees the public decisions of the previous ones, but not the private information of the earlier. That's very important, because if they would see all the private information, there would be no cascades. The cascade is because the public kind of masks the private. By using Bayes' rule, we define the formal model, and we showed that even if people decide rationally, using all the information they have, you can get information cascades. So a small amount of information will force all the decisions to be the same, and it's even often incorrect. Another approach, which is independent decision making, does not lead to these kind of cascades, and it can be better. To avoid cascades, you can introduce independence. Of course, on the internet, that's not always possible, because people will see what the previous people did. The only way would be to hide the person's decisions for a long time, or to make some of the private information of each person visible. That's very hard in general, but if you can do it, you should try to make the decisions independent and not sequential. Okay, and this happens a lot in the real world. So the formal model is simple, but the real world is it's behaving almost like that. The one nice thing about cascades is that they're fragile and you can break them. So if you see a cascade happening and you know it's wrong, you can break it by adding more information. Okay? by giving people extra information, you can break it. Okay? Okay, so that's where I'm going to end today. And so this is information cascade. Next time we're going to talk about direct benefit cascade, which is a different kind of cascade, and then the effective network structure. Sometimes you have like bottlenecks on the network, where you have like one or a few people are like bottlenecking between two parts of the network, and this can also cause things to block and cascades to form. Huh? So we're going to look at that too. Okay, and remember I gave you a few numerical algebra exercises to do. So try to do some of that. So the complicated formula that I showed you, the book actually explains it, and actually if I had, I could do it in 15 or 20 minutes. But I don't want to. I want you guys to look at it. So please try to do some of the exercises so that you really understand how the numbers are changing, huh? In this formula, for example, or the more general one. Okay? Okay, so now we're 10 minutes before 4, but I think I'm going to stop here. I think we have enough. We have, this is the lecture I wanted to give. So let me stop here for today. See you guys next week.